So welcome back to the next lecture on automated program verification. So just to give a roadmap, right, of what we have done so far. So our goal was to study automated program verification, right? In particular, this paradigm, right, of verification, which is called deductive verification, right? So deductive verification uses proof rules, right, in order to construct the proof of correctness of a program, and it uses constraint solvers, right, in order to discharge the proof of correctness, right. So basically, we want to express the verification problem using mathematical logic, right, using uh, propositional logic and first order logic, right. So we first studied propositional logic, which is quite powerful, right, but is not as expressive as first order logic, right. So in first order logic, you can express concepts more easily, right, because you have access to things like functions, right, variables, constants, and predicates, which are not available, let's say, in propositional logic, right. So if you want to, for example, consider the set of integers, right, set of natural numbers, right, and you want to write down, let's say, some properties of integers or natural numbers, right, mathematically, right, using logic, then it's very hard to do so in propositional logic, but we can do that in first order logic, right, because you can have constants, right, to represent the various numbers and so on. Okay, so going forward in that particular direction, right, today we are going to look at this notion of a first order theory, right, and a first order theory uh, is what is going to give meaning, right, to some specific concepts that we have in mind, right. So we know that in general in first order logic, you have predicates and functions, right, and these predicates and functions can have arbitrary arity, right, and you can define as many new predicates and functions as you want and use them as part of your formula, but they are in general uninterpreted, right. Uninterpreted meaning that they don't have a meaning, right. So you give an interpretation to give a meaning to a function or a predicate, but you can always give like different interpretations, right. So there are, there are an unbounded, right, infinite number of interpretations that you can give to any function or predicate symbol that is used in the formula, right. But in practice, right, we have some specific predicates and functions, right, for which we have a specific meaning in mind, right. So for example, if you look at the integers, right, set of integers or natural numbers, then we have these functions such as addition, right, plus multiplication, division, and so on, right. And similarly, you have this binary predicates, right, such as the equal to predicate, the less than or equal to predicate, right, and so on. So again, right, thinking purely in terms of first order logic, these are just predicates and functions, right. So in principle, right, you can assign any interpretation, right, to these symbols, but we want to assign a very specific interpretation, right. So we want to say, for example, that plus is just a integer addition, right. Its meaning should be restricted to be just integer addition, right. So you should not be able to say like 1 plus 1 equal to 3, right. You must say 1 plus 1 equal to 2. Okay, similarly 1 is always less than or equal to 2, right. You don't want to say that 2 is less than or equal to 1, right. So we want to give a specific meaning to these symbols, and we can give a specific meaning, right, which means we can fix an interpretation, right, using the notion of a first order theory, right. So first order theory allows us to formalize the meaning, right, of certain structures, right, for which we have a specific meaning in mind. So first, let us look at a general definition of a first order theory, right, and then we will see specific instances, right, of, for example, the theory of equality, the theory of integers, and so on. Okay, so in general, what is a first order theory? So a first order theory is defined by two components, right. So it has a signature and it has axioms. Okay, so a signature, which we denote by this symbol sigma t, this just contains all the symbols, right, that are defined by the theory. So constant, predicate, and function symbols that will be defined by the theory. The definition, right, the meaning of these symbols is given by the axioms, right. So the axioms themselves are FOL formula, right, which contain only the symbols which are present in sigma t, right. So the meaning of these symbols we are going to formally encode again using first order logic formula, right. and this formula will be closed, right, meaning that they won't have any free variables, right, and they will only contain the symbols from sigma t. So now given a theory, right, which is a signature and a set of axioms, you can now construct other formulas, right, which only contain the symbols from the theory, right. So we say that a sigma t formula is another FOL formula, right, which only contains symbols from the signature sigma t. Okay. So once you have defined this theory, right, which is just a set of symbols and a set of formula which give meaning to those symbols, right. Now given an arbitrary FOL formula which is a sigma t formula, right, which means it contains symbols from the signature, right, from the theory, is such a formula satisfiable, or is such a formula valid, right. So we will consider the notion of satisfiability and validity, but modulo the theory. So what does that mean, right? So now given an interpretation I, right, so you take any interpretation I, we say that such an interpretation I is a T interpretation if it satisfies all the axioms of the theory T. Okay. So the theory T has defined some symbols, right, and it has also defined some axioms, right, which are some FOL formula. So an interpretation I, right, which will assign values to those symbols is called a T interpretation if it satisfies all the axioms of the theory, right. So this is what we want, right. In fact, so we want an interpretation which only satisfies the axioms of the theory, right, because the axioms of the theory give an intended meaning to the symbols of the theory, right, to the signature of the theory. Okay. So an interpretation I is called a T interpretation if it satisfies all the axioms of the theory. So formally this means that if you take the set of axioms AT, then for every axiom A, I is a model of A, right, which means that A evaluates to true, right, under I. So we'll only focus now on interpretations which are T interpretations, right, which means that which satisfy the axioms of the theory. Okay. So now given some sigma T formula F, okay, we say that this formula F is satisfiable modulo T, right, if there is a T interpretation that satisfies F. Okay. So note the difference, right, between this definition and the definition of satisfiability that we had seen earlier, right. So we said a formula is satisfiable if there is some interpretation which is a model of the formula, but here we say that a formula is satisfiable modulo T if there is a T interpretation, right, which means there is an interpretation which satisfies all the axioms of the theory, and such an interpretation should be a model of F, right, should also satisfy F, right. Then we say that the formula F is satisfiable modulo T. Analogously, we say that formula F is valid modulo T if every T interpretation satisfies F, right. So you take all the T interpretations, right, every interpretation which satisfies all the axioms of the theory, right, every such T interpretation should also be a model of the formula F. It should satisfy F. So in which case we say that the formula F is valid modulo T. So here we introduce a slightly new notation, right. So we say that T entails F, right. So you should read this as entails, okay, which means that T implies F, right. So all the axioms of the theory T, right, imply the formula F, which means that every T interpretation satisfies the formula F, right. Every T interpretation is a model of the formula F. Okay. So we read this as entails. So in order to further understand, right, this difference between satisfiability, validity, and satisfiability and validity modulo the theory, right, let's consider this couple of questions, right. What is the relationship between satisfiability and satisfiability modulo a theory? Okay. So which of these two following results hold, right? If F is satisfiable, does that imply that F is satisfiable modulo T, or the other way around, right? If F is satisfiable modulo T, does that imply that F is satisfiable? So you can see that from the two definitions, right, the first result doesn't hold, right, but the second result holds, right. So this is because if F is satisfiable, that just means that there is some interpretation which is a model of F, but such an interpretation may not be a T interpretation, right. So if you want to say that F is satisfiable modulo T, then there must exist a T interpretation, right, which means an interpretation which obeys all the axioms of the theory, right? So only if such an interpretation exists and it is a model of f, then we say that f is satisfiable modulo t. Okay. However, if f is satisfiable modulo t, then that does imply that f is satisfiable, right? Because there exists some interpretation, right? It's in fact it's a special interpretation, right? It's a t interpretation under which f is satisfied, right? F evaluates to true. Similarly, let's consider the difference between validity and validity modulo t. Okay. So which of these two following results hold? So if f is valid, does that imply that f is valid modulo t? Or if f is valid modulo t, does that imply that f is valid? Okay. So here the answer is reversed, right? In a sense that the first one is true, but the second one is false. Okay, so intuitively, right, if f is valid, that means that every interpretation, right, no matter what interpretation you take, is a model of f, which means that every t interpretation, right, which is going to be a subset of the set of all interpretations, right, because a t interpretation should also satisfy the axioms of the theory, right. So if every interpretation is a model of f, it means every t interpretation is also a model of f. That means that f is valid modulo t, right. On the other hand, if f is valid modulo t, that doesn't imply that f is valid in general, right, because only t interpretations are models of f, right. Any arbitrary interpretation need not be a model of f. Okay. Okay. So the reason why we have well, one of the reasons, right, why we are focusing on the notion of satisfiability or validity modulo theory, right, is because we want to get decidability. Right? So we have seen in the last lecture that first order logic, right, the satisfiability and the validity problem in general is undecidable, right, which means that you cannot have a decision procedure, right, which will take as input an FOL formula and output yes, the formula is satisfiable, or no, the formula is not satisfiable. Right? Similarly for validity. So as it so happens, right, the satisfiability or the validity problem modulo a theory, right, depends on the axioms of the theory, right, which means that there are theories for which this problem is decidable, right, and this is good news for us because we want a decision procedure, right, so that we can reduce the verification problem, right, to the satisfiability or the validity modulo the theory problem, and then we can use these decision procedures, right, for that problem for verification. Okay. So first let us define this notion of completeness. So we say that a theory T is complete if for every closed formula f, either f or negation of f is valid modulo T. Okay. So you take every closed formula f. Okay. So in particular you will take a sigma T formula, right, which is a formula constructed using the symbols, right, of the theory, right. And if you take any such formula f, right, either f is valid or not of f is valid modulo T. Right. So this is a very strong statement, right. It's saying that no matter what formula, any closed formula you construct, right, using the symbols of the theory, either that formula is going to be valid modulo T or its negation is going to be valid modulo T. Right. If this is the case, then the theory T is said to be complete. Right. So formally this means that either T entails f or T entails not of f. So this completeness is a very strong property, right, and only very few theories satisfy this property. Okay. So for example, we can look at the empty theory, right. So the empty theory is a theory which doesn't have any specific or any special symbols, right. So it doesn't have any axioms at all. So the set of axioms is empty and it doesn't have any special signature, right. So this empty theory is nothing but the entirety of first order logic, right, because if you think about the entirety of first order logic, right, it doesn't in FOL in general, every function symbol, every predicate symbol is uninterpreted, right? So you don't have a specific meaning in mind for every or rather for any function symbol or predicate symbol, right, or for any constant as well. Okay. So because there are no axioms at all, right, every interpretation, right, is a T interpretation, right, is an interpretation of the empty theory. Okay, because the set of axioms themselves are empty. Okay. So now for this empty theory, which is nothing but the entirety of FOL, you can ask this question, right, is it complete or not? Okay. Which means that is it the case that if you take any closed formula, either that closed formula is valid or its negation is valid, right, and modulo T here doesn't come into the picture because the theory itself is empty, right? So there are no axioms at all, right? Which means that if the formula is valid, then it's also valid modulo t, and vice versa. Okay. So if you think about this question, right, are there formulas, right? Are there closed formulas for which either that formula is valid or its negation is valid, right? So this is clearly not true, right? Because for example, I can just consider the simple formula, there exists x px. So this formula is not valid, right? Because why is it not valid? So there is an interpretation, right, which falsifies this formula, right? So if I consider, let's say, this interpretation I, right, whose domain only contains one element, right, and the assignment of P, right, assigns, let's say, that A to false. Right. So now this, so what I claim is that this particular interpretation I, right, is not a model of there exists x px, right? And it's quite clear to see, right, because for I to be a model of there exists x px, there should be an element in the domain of I, right, for which on which applying this predicate evaluates to true, right, but there is no such element, right? So therefore this formula is not valid under the empty theory. What about its negation, right? So if you take its negation of there exists x px, right, so this formula is also not valid, right? Again, there is an interpretation which will falsify this formula, right, which means that under that interpretation, right, that interpretation is not going to be a model of this formula. Okay. So no, there exists, so we have seen this equivalence last time, right? This negation of there exists x px, this is equivalent to for all x not of px. Okay. So how do I show, right, that this particular formula is not valid? So I need to show a falsifying interpretation, right, which means that I need to show an interpretation which is not a model of this formula, right, which means that if I consider, let's say, the same interpretation I, right, let's say I prime, where my domain only contains one element, right, but the assignment, right, for this P assigns A to true. Okay. So what I claim is that I prime is not a model of not of there exists x px, and this is because this not, right, these two nots will cancel, right? So essentially I prime is a model of there exists x px, right, and this is true in fact because I can take the assignment of x to be equal to a, in which case p of a evaluates to true, right? So the goal, I mean the takeaway from this entire exercise, right, is that this formula which is there exists x px is not valid under the empty theory, and neither is its negation valid, right? So the FOL, right, which is the empty theory, is not complete, right? But there are other theories which are complete, right? So we will see in fact, right, later on that theory of natural numbers, for example, is a complete theory, right? Which means if you take any closed formula, either that formula is valid or its negation is valid modulo the theory. So this is the example that we had considered. Okay, so now a theory is decidable if this entailment question, right, the validity problem, right, which means if T entails F, right, is F valid modulo T, is decidable for every formula F. Okay. So the validity problem modulo the theory is decidable for every formula F. Okay. If that is the case, then we say that the theory is decidable. Okay. So the FOL, the entirety of FOL, right, which is the empty theory, is undecidable, right, which means that not all theories are decidable, right, but there are various useful theories which are actually decidable, and we will look at some of them.